Lecture 29, Transition Metal Complexes, Stereoisomers and Crystal Field Theory. Last lecture, we started taking a look at isomers of different transition metal complexes. Remember that isomers, two molecules are isomers if they have the same molecular formula, but somehow different structures. We first took a look at structural isomers where the bonding is different between the two isomers. We looked at coordination sphere isomers where where ligands and counter ions switch places. We also took a look at linkage isomers where a single ligand bonds to the transition metal ion through different atoms. Now we're going to take a look at stereoisomers. Stereoisomers are interesting because they have everything is bonded the exact same way in each transition metal complex. That is, that if you count up the different types of bonds that are in both isomers, they're going to be the same. However, if you look at the complex ion, you'll see that the ligands actually have different spatial arrangements. That is, they're in different positions in three-dimensional space around the transition metal ion. There are two main types of stereoisomers that are observed in transition metal complexes. The first type are geometric isomers, which simply are isomers in which the ligands have different spatial arrangements around the metal cation. We're going to look at two examples of geometric isomers. The first example are cis and trans isomers. Cis and trans isomers occur in octahedral complexes, usually when you have 4 of one type of ligand and 2 of another type of ligand. The 2 of the same one type of ligand occupy different positions around the coordination sphere of the metal cation. For cis isomers, the 2 ligands are 90 degrees away from one another and appear on both sides or on one side of the complex ion. In the picture, we show 2 different ways that you can have cis isomers. There are other ways as long as, again, there is a 90-degree angle between the ligands. In trans isomers, the ligands are on opposite sides of the molecule, having a 180-degree angle between them. Once again, there are different ways to position the ligands so that they are trans from one another, but they will be trans as long as there's a 180-degree angle between the ligands. Here are real examples of cis and trans isomers for octahedral complexes. In the cis example, you'll notice that the chlorine ions, the chlorine ligands, are at a 90-degree angle from one another, which gives rise to the cis isomer. For the trans example, the chlorine ligands are 180 degrees from one another. You can also have cis and trans isomers in square planar complexes. Here's a famous example. There are two complexes that form between platinum, chlorine, and ammonia ligands. The cis isomer, known as cisplatin, is a popular therapeutic drug to treat cancer patients and is typically included in some chemotherapy treatments. The trans isomer, transplatin, with the chlorine and ammonia ligands 180 degrees from one another, is the other isomer, which is actually toxic to humans. Fortunately, these two isomers can be separated through processes that utilize boiling point and melting point, such as distillation. Since the cis molecule is a bit more polar than the trans molecule. The other type of stereoisomers occur when you have 3 of one type of ligand and 3 of another type of ligand. These are called FAC and MER isomers, where FAC is short for facet or face, and MER is short for meridian. To understand these isomers, you can take a look at the octahedron shape, which is the shape that you get when you connect the ligands together in an octahedral transition metal complex. In a FAC isomer, the 3 ligands are positioned around the triangular face of an octahedron. As with the cis and trans isomers, there are a few ways that you can do this. In a MER isomer, the 3 ligands are now positioned around the edge of the octahedral shape. Here are some real examples of FAC and MER isomers. You can see that in a FAC isomer, the chlorine and ammonia ligands are on the face or facet of the octahedral shape, while in the MER isomer, the chlorine and the ammonia ligands are around the edges of the octahedral shape. The second class of stereoisomers are very common in both transition metal complexes, but also in organic complexes, which is why I want to introduce the idea here. These are optical isomers. Optical isomers are mirror images of one another. Here's an example of optical isomers of a transitional complex that contains chloro and ethylene diamine ligands. It's important to note that this complex also has cis and trans isomers. However, the cis isomer has an optical isomer, that is, an isomer that's its mirror image. The mirror image is not superimposable, or you cannot overlap the structures and get the same structure. A good example of a real life example of something that 2 things that are optical isomers are your hands. Your hands are mirror images of one another, and you cannot superimpose one hand on the other. One of the few ways that you can detect optical isomers is how they react to polarized light. We call this property of molecules chirality. And as I said, when you go on to take organic chemistry, you'll see more examples of chiral molecules. Please note that you do not need to know how to recognize whether or not a transition metal complex has optical isomers, since that's a bit beyond the scope of this course. We just want you to know that they exist. Now we're ready to move on to looking at different properties of transition metal complexes, besides the stereoisomerization and periodic properties. We're going to look at these properties in terms of what's known as crystal field theory. Crystal field theory is a model for bonding for transition metal complexes that is useful in 2 avenues. First is looking at magnetic properties of transition metal complexes, and the second is looking at spectroscopic properties, i.e. the color of the solid or aqueous form of the complex ion. Crystal field theory is a basic theory that's based on electrostatic interactions between the metal's d electrons and the lone pairs on the ligands. Remember that an electrostatic interaction is the interaction between particles that have charge. An important thing to remember is that if the charges are alike, then they will repel one another, and that increases the energy of your system. For charges that are not alike or opposite, the two charges will attract one another, which lowers the energy of the system. For crystal field theory, we're most interested in electrostatic repulsion, since we're dealing with electrons from both the metal cation and the ligands, which will repel one another. We're going to describe crystal field theory for octahedral complexes, which are the majority of the complexes you'll see in this unit. One important thing to remember is that for metal cations, d orbitals, if the cation is not surrounded by ligands, those d orbitals all have the same energy. However, if you take the metal cation and surround it with ligands that have an octahedral geometry, you're going to start to increase the energy of all of the d orbitals. But some d orbitals are going to increase in energy more due to their interactions between the ligands. This is generally going to happen if the d orbitals have lobes that point directly at the ligands. Let's take a look at the d orbitals relative to those ligands. There are two types of d orbitals, the dz squared and the dx squared minus y squared ligands, orbitals, that will experience a very large increase in energy. If you look at the pictures on the right, you'll see that these orbitals both have lobes that point directly at the ligands, which are represented by the grayish spheres. This increase in electrostatic repulsion will cause those orbitals to go up in energy by quite a bit. There are three other d orbitals in which the lobes of those orbitals point between the ligands. Although there will still be some electron repulsion that will increase the energy of the orbitals, this increase will be much smaller because the orbitals are not interacting directly with the ligands. This causes a split in the d orbital energies, as shown in the picture on the top right. The dxz, dyz, and dxy orbitals undergo a smaller increase in energy than the dx squared minus y squared and dz squared orbitals. This results in three orbitals having a lower energy than two of the other orbitals. This breaks the degeneracy or same energy of the d orbitals once the metal cation is surrounded by ligands. Note that it's not important for you to know which orbitals go up in energy more than the others, but know that the d orbitals do split in energy so that three orbitals have a lower energy than two other orbitals. The difference in energy between these two sets of d orbitals is known as the crystal field splitting energy for octahedral complexes, or delta O. Now, you might ask, what determines how big or small delta O is? It turns out there are a lot of things that do impact delta O, such as the nature and charge of the metal cation and the ligands. But mainly, what we'll look at is the effect of the ligands. There are ligands that interact very strongly with the metal cation and cause a large difference in energy between the split orbitals. We call these strong field ligands. Other ligands do not bond strongly or interact strongly with the metal cation, which means that they create a smaller delta O. We call these ligands weak field ligands. So how do we know which ligands are weak field and which ones are strong field? There exists an empirical listing of ligands in order of increasing delta O called the spectrochemical series. This spectrochemical series that I'm about to show you are just for ligands. There are different spectrochemical series for metal cations, which we won't discuss in this course. Here's the spectrochemical series for ligands. The ligands that are further to the left are weak field ligands, and they increase in field strength as you go from left to right. Notice that halogens, iodine, bromine, chlorine, and fluorine, are considered weak field ligands, along with hydroxide and water. Strong field ligands include ammonia, ethylene-diamine, the nitro ligand, cyano, and carbon monoxide. It's important to note that carbon monoxide is the stronger field ligand. It is actually a stronger field ligand than the oxygen molecule itself. This is important when studying carbon monoxide poisoning. Since carbon monoxide is a stronger field ligand, it binds to the iron in the hemoglobin in your bloodstream much more strongly than oxygen is bonds, which means that when exposed to carbon monoxide, your blood is more likely to latch on to CO, which causes the poisoning. The only way to reverse carbon monoxide poisoning is to place the patient in a hyperbaric chamber where the oxygen pressures are very large. This thermodynamically reverses the effects of carbon monoxide poisoning. Now let's look at how delta O affects the color of coordination compounds. You might remember from your absorption spectral lab that the reason why we observe different colors of objects is due to the absorption and transmission of visible light. For example, if we take a look at this picture of a complex ion, we see that it's a deep purplish blue color. If we measure an absorption spectrum, we find one peak that's right around that occurs right around 500 nanometers around the green region of the visible spectrum. We see that the absorption is very low at the red and blue extremes of the visible spectrum, and red and blue come together to form purple. The low absorption portions of the spectrum give rise to the observed color of the solution, while we don't see the absorbed wavelengths of light. So how does this relate to our delta O? If you have complex ions that have a small delta O, they'll absorb light that has a low energy. Low energy light has longer wavelengths. Since these complexes are absorbing long wavelengths of light, the complex ion will typically reflect or transmit light with short wavelengths or higher energies, meaning that the color will appear more blue shifted. If you have a complex ion that has a larger delta O, it's going to absorb higher energy light or shorter wavelength light, leaving the longer wavelength light to be reflected or transmitted by the solution. This means that the color will appear more red shifted. Here's an example of how the spectra of a complex ion can be affected by different ligands that are placed on it. This figure shows different nickel complexes with different ligands. You'll see that the complex ion formed between nickel and chlorine has an absorption peak at a longer wavelength. This is because chlorine is a weaker field ligand. That meaning that this complex ion is absorbing the longer wavelengths of light or lower energy wavelengths of light and transmitting longer wavelengths of light. It turns out this complex ion appears more a yellow-green color. At the opposite end, the nickel complex with the En ligands absorbs light at the shortest wavelength of these four complexes. This means that it's absorbing more longer wavelength light. You'll see that the low absorbance occurs in the purple end and on the red end of the spectrum, giving rise to a purple color. So therefore, delta O can affect the color of the complex ions based on the wavelengths of light that's absorbed and transmitted. The other property that is affected by the size of delta O is the number of unpaired electrons observed for the complex ion, giving rise to what we call high and low spin complexes. There's a competition between delta O and the energy it takes to pair up electrons within the same orbital. If delta O ends up being larger than the electron pairing energy, then when the electrons occupy the d orbitals, they're going to strictly follow the Aufbau principle, meaning that they will occupy the lower energy orbitals first and then start to pair up, since that energy is less than actually moving to another energy level. This is what results in what we call a low spin complex, which minimizes the number of unpaired electrons. When delta O is smaller than the electron pairing energy, then it actually takes less energy to put the electrons in a higher energy orbital than to actually pair them up within the same orbital. This means that the complex ion will maximize the number of unpaired electrons, and this will result in a high spin complex. Please note that high spin and low spin are pretty relative to one another. This doesn't mean that low spin complexes won't have unpaired electrons. It just means it will minimize the number of unpaired electrons for a given electron configuration. We can use the spectrochemical series to look at which ligands are most likely to cause high spin and low spin complexes. High spin complexes will tend to occur with weaker filled ligands, while low spin complexes will tend to occur for stronger filled ligands. Here's a good example. Here are two complexes that contain cobalt 3+, giving us 6d electrons. The complex ion on the left-hand side contains fluorine ligands, which are considered to be weak filled. You see that there are 4 unpaired electrons in the orbital occupation diagram for the cobalt ion, showing that this complex is a high spin complex, since the delta O is less than the energy it takes to pair up the electrons in an orbital. On the right-hand side, we have cobalt complex with ammonia, and ammonia is a stronger filled ligand. This shows that all of the electrons are paired up in the lower energy d orbital level. This results in a low spin complex. These two complexes are distinguishable not only by their color, but also by their magnetism. We can do an experiment called an EPR experiment, or electron paramagnetic resonance experiment, which allows us to detect the number of unpaired electrons. The high spin complex will react more strongly with the magnetic field than the low spin complex, which will allow us to detect the number of unpaired electrons. Let's take a look at an example. We have two cobalt complexes. Two complexes. Cobalt with ammonia ligands and an iron with water ligands. We note that the cobalt complex is diamagnetic and the iron complex is paramagnetic. We have two parts to this problem. We first want to draw orbital occupation diagrams for both complex ions, and we then want to determine which complex is going to have a higher delta O. So, before we draw our occupation diagram, we need to know how many electrons are present in the d orbitals of both metals. This means that we need to write an electron configuration for the metal ion. We note that ammonia and water are neutral molecules and do not contribute to the charge of the complex ion. Therefore, cobalt has a 3+ oxidation state or charge, and iron has a +2 charge. The electron configuration for cobalt 3+ is argon 3d6, and for iron it's also argon 3d6. This is nice because it's a means of comparison since both complexes have the same number of d electrons. Now to draw our orbital occupation diagrams, we need to figure out which complex is high spin and which is low spin. We use some of the information from the problem. You might recall that diamagnetic means that the species is weakly repelled by a magnetic field. This usually occurs when there are no unpaired electrons in the structure of the molecule or atom. This means that we expect that a diamagnetic complex ion is going to be low spin, especially in the case where there's an even number of electrons, as there are here. For paramagnetic complex ions, this means that there's at least one unpaired electron present. These ions are weakly attracted to a magnetic field. This means that the iron complex has to be a high spin complex. Now let's draw our orbital occupation diagrams. So remember, you're only responsible for knowing that there are 3d orbitals that are lower in energy than the other two. Therefore, there's a 2-3 splitting. For a low spin complex, it's best to start by following Hund's rule, which means for orbitals that have the same energy, you put one electron in each orbital with the same spin. However, when we get to the end of that energy level, we need to decide whether or not we put the electrons in a higher energy level or start pairing them up in the lower energy level. Since we know that this complex is a low spin complex, we know that it takes less energy to pair the electrons up in the same orbital than it takes to actually put the electrons in a higher energy orbital. Therefore, we just go back and pair up the 3 electrons with the remaining 3 electrons. For our high spin example, we start out the same way by following Hund's rule, putting 1 electron in each of the lower energy orbitals, which also follows the Aufbau principle. Now for a high spin complex, we note that the delta O is smaller than the energy that it takes to pair up the electrons. Therefore, it takes less energy to put the electrons in the higher energy level than it does to pair up the electrons. We've now used up 5 of our 6 d electrons. So what do we do with electron number 6? Now it's time to start pairing up, and we go back down to the lower energy level and pair up one of the electrons with the last electron there. So now we have our orbital occupation diagrams for both complex ions. The second part of the question asks us to figure out which complex ion has the higher delta O. We can take a look at our spectrochemical series. When we find water and ammonia on the spectrochemical series, we find that water is farther to the left than ammonia is. This means that ammonia causes a bigger delta O than water does, which answers our second question. Although we're going to focus on crystal field theory for octahedral complexes, I also want to show you that crystal field theory also works for complexes that have different geometries. Remember that the way that the d orbitals change in energy depends on the electrostatic repulsion between the metal's electrons in d orbitals and the electrons that are being shared through the ligands. For a tetrahedral complex, in which the four ligands make a tetrahedral shape, the d orbital splitting pattern is exact opposite of the octahedral, meaning that dx squared minus y squared and dz squared are lower in energy than the dxy, dxz, and dyz orbitals. The difference in energy between the two sets of orbitals is now known as the crystal field splitting energy for tetrahedral molecules, or delta T. Since there are less ligands, delta T is much less than delta O is for the four ligands. As a consequence, most tetrahedral complexes tend to be high-spin complexes. The other common geometry that we see for transition metal complexes are square planar complexes. There are multiple energy levels for the d orbitals in a square planar field. And we find that there are actually 3, not 4. There are 3 different deltas, meaning that they split into 4 different energy levels. Most square planar complexes are low spin due to the complex splitting pattern. Remember, as I said, we're going to focus mostly on octahedral. Well, guys, this is our last lecture. And I know it's been a strange semester for both you guys and for myself. But, I think you guys have done a pretty good job adjusting. I know it's been hard, but it's been pretty good. And I enjoyed having you guys as a class, and wish you guys all the luck in the world. So we're going to start preparing for our final, so look for some information about that. But you guys have been a pleasure teaching, so hope you guys take care and good luck with your future plans. Okay, and I guess have a good summer.